Vectors you can understand and use in minutes. By the end, you will build tiny numpy vectors, measure their length, and compare items using dot product and cosine similarity. You will also retrieve the top 3 matches from a small set and see how normalization changes the winner. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Vectors matter because they let models compare meaning. A code property we use is similarity, and 2 common metrics are raw dot product and cosine similarity. The trade-off is simple. Dot product favors magnitude, while cosine favors direction. This approach scales easily to hundreds or thousands of embeddings, but for millions, you will need an index or approximate search to keep latency reasonable. At a high level, vectors shine when you want compact numeric summaries of items and fast similarity checks. They are simple to store and add, but a limitation is that magnitude can hide alignment unless you normalize. We will build a tiny NumPy demo that prints a vector length, shows a shift, ranks by dot product, ranks by cosine, and returns the top 3 matches. First, we will create a tiny vector and measure its size. This snippet builds a tiny vector and prints its Euclidean length. The code imports NumPy and defines the variable v as a one-dimensional array, a basic numeric container for vector math. The numpy.linalg norm computes the Euclidean length, which is the square root of the sum of squared components. And the snippet rounds the length so it is easy to read aloud. It prints the original vector converted to a plain list and the rounded length, so you can see how the numeric components turn into a single size value used in many AI calculations. Next, we nudge that vector to see element-wise effects. This snippet adds 2 vectors element-wise to show a simple transformation. It reuses the variable v and defines w as offsets that nudge each component up or down. Then the expression v plus w performs element-wise addition, which updates each coordinate independently. The resulting vector is stored in S, and numpy round keeps numbers short, so the change is easy to inspect. The print shows the new coordinates after shifting the original vector by w, and that element-wise operation is the core building block behind model updates and simple residual connections. Now we rank a small set of items against a query. This snippet ranks items by raw dot product with a query vector. The variable x holds 3 item vectors as rows, and the variable q is a query. Using the @ operator computes dot products between each row of x and q, giving a similarity score per item in Sims. And the dot product measures magnitude, weighted projection of one vector onto another. The numpy argmax function finds the index of the highest score, which represents the best match under this metric. The code prints the winning row index and its rounded score, so you see which item aligns most strongly by magnitude. Then we'll normalize to compare only direction. This snippet switches to cosine similarity by normalizing vector lengths. It reuses the matrix specs and the query q, then divides each dot product by the product of their lengths using numpy.linalg norm, which removes magnitude effects and focuses on direction. Cosine similarity measures how aligned 2 vectors are and returns values between -1 and 1, so it highlights directional agreement rather than size. The Sims variable now holds those cosine scores, and numpy argmax returns the cosine best row. You can observe how a large vector that 1 under dot product can lose once normalization emphasizes alignment. Finally, we return the top 3 matches by similarity. This snippet returns the top 3 most similar items using cosine similarity. It computes cosine scores in S by dividing dot products by the product of norms, so only direction matters, and then numpy argsort sorts indices by score. The negative sign flips the sort order so the highest scores come first, and slicing the first 3 entries picks the top 3. A list comprehension builds readable pairs of index and rounded score for display. If you increase the slice length, you get more results at the cost of extra output. If you decrease it, you see fewer matches, which is an adjustable trade-off between recall and compactness. Quick recap. Vectors let you encode items as numbers, compare them with dot product or cosine, and retrieve matches by sorting similarity. Use raw dot product when magnitude matters. Use cosine when direction matters, and you want fairness across lengths. One caveat. This simple NumPy approach is fine at small scale, but large collections need indexing or approximate search to stay fast. Next step, scale the same pipeline to a larger corpus and add timing and accuracy checks so you can measure how retrieval time and match quality change as you increase the dataset size. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.